In today's video, we're going to move on with this idea of how do we actually use derivatives, but today we're going to be focusing on the second derivative and asking ourselves that question of what does the second derivative actually tell us? Well, to help us answer that question, let's review what we know about derivatives. First of all, what does the first derivative tell us? The first derivative expresses how a function changes. It's an instantaneous rate of change. So that's what the first derivative tells us, but what about the second derivative? We kind of talked about this in 1.8 when we talked about higher order derivatives, but the second derivative expresses how the derivative changes. So what does this mean? If the second derivative is positive, that means the derivative is increasing. If the second derivative is negative, that means the derivative is decreasing. But what's happening if the derivative is increasing? Let's look at a graph. Let's look at what this looks like visually. So let's say we have an increasing function. If I just draw a straight line, the derivative in this case would be constant because I have a linear function where the slope is constant and the derivative is really just the instantaneous slope. So for this linear function, the slope isn't changing, and therefore the second derivative is 0 because the derivative is not changing. The derivative is staying the same. So let's change this up a bit and assume that my second derivative is positive. I'm still going to have an increasing function, but if the second derivative is positive, that means my rate of change is increasing. If I'm thinking about rate of changes or slope, if it's increasing, that means it's getting steeper. So it gives me this shape. This would be an increasing function, or a function with a positive first derivative. Right, we covered that in our previous video. And a positive second derivative. Well, let's do one more example. What if my second derivative is negative? I'm going to keep going with this. I'm still going to assume that we have a positive first derivative, meaning what? Meaning my function is increasing. But how are things going to change if I say that my second derivative is negative? What would that mean? If my second derivative is negative, that means your derivative is decreasing, or your rate of change is decreasing. Therefore, my slope isn't getting steeper, it's getting more shallow. So that would look something like, notice how my function is still increasing, but now the slope is getting shallower and shallower as it goes along. So looking at these graphs, can we now maybe answer that question of what does the second derivative tell us? Well, it turns out that the second derivative determines curvature. Notice when my second derivative was 0, what type of curvature did I have? I didn't have any curvature. I had a straight line. If I have positive second derivative, I get positive upwards curvature, or we call this concave up. This upwards curvature. If my second derivative is negative, I have downwards curvature, which we call concave down. And that's where this word concavity comes from. It's this idea of concave up or concave down. So that's what the second derivative actually helps me determine with a graph, how the derivative is curving, whether it's curving up or whether it's curving down. If you want to make sure you understand this whole concavity idea, I'd challenge you to try the same exercise, draw 3 different pictures, but with a decreasing function instead. So assume you have a negative first derivative, meaning you have a decreasing function, and then draw 3 different pictures of functions that have a second derivative of 0, a positive second derivative, and a negative second derivative, and see what that does to the shape of the graph. Regardless, let's move on. So that means that if we combine what we learned in the previous video in 2.1 with what we've learned now in 2.2 about the second derivative, that means using derivatives, we can get a really good idea of what a graph looks like without having to rely on a graphing calculator or something to actually graph it for me. Because let's look at the 4 things that we can now determine just based on derivatives. First, we can determine relative extrema. How do we do this? We can do this by simply finding critical points, because my relative extrema occur at the critical points. And how do I find the critical points? That's by setting the derivative of the function equal to 0. Or looking where the derivative is undefined. Okay, so that's the first thing I can determine using derivatives. The second thing I can determine is intervals of increasing or decreasing. What am I using to determine this? Well, I'm still using that first derivative, because wherever the first derivative is positive, I have an increasing interval. And wherever my first derivative is negative, I have a decreasing interval. So this is really closely related to that first derivative test that we talked about in the previous video. Once I know my critical points, I can create a number line and create different intervals that are separated by my critical points. And then I can test each interval. I can test the first derivative to determine if each of those intervals are increasing or decreasing. So both of these, so far, these two things are related to that first derivative. But now that we know about the second derivative, I can keep going. Using the second derivative, I can determine what are called inflection points. So this is a new term, and these inflection points are closely related to critical points because they represent spots where the second derivative is equal to 0 or undefined. And what makes a point an inflection point? An inflection point, the actual definition, is points where the concavity changes. So that's what an inflection point actually is. It's a point where concavity changes. And notice how this is very similar to what we did with the first derivative. First derivative tells me about increasing and decreasing, and those critical points represents the spots where my graph can change from increasing to decreasing. And so a similar thing is happening with your second derivative. Your second derivative is telling you about whether you have upwards curvature or downwards curvature, and these inflection points represent spots where that curvature can change. So that's what an inflection point is. And I can find those easily by just finding the second derivative and setting it equal to 0. Well, now that I know my possible inflection points, I can then find my intervals of concavity. I can figure out whether spots where I'm concave up or I have upwards curvature, and intervals where I'm concave down or I have downwards curvature. And to test that, I'm going to do something very, very similar to what I did in the first derivative test. I'm going to create a number line and put my inflection points on the number line and then test points inside each of the other intervals. But instead of testing them with the first derivative, I'm going to test them with the second derivative. Because what will the second derivative tell me? It'll tell me the concavity at those points. And so by testing those in the second derivative, I can determine whether I'm concave up or concave down inside these intervals. Now you might think that this right here is just called the second derivative test, but unfortunately, that's not the case. We actually don't have a name for this kind of test. It's really just the same thing as the first derivative test, except you're doing everything with the second derivative. The reason why we don't call it the second derivative test is I actually have something called the second derivative test that tests something different. Before we move on to the second derivative test, don't worry, we will go through an example of this for a specific function in the examples video. So if you're curious about what this looks like with an actual function, I'll go through one of those in the examples video. But let's talk about the second derivative test. What is the second derivative test? Well, the second derivative test is another way to test relative extrema. It's another way to test whether critical points represent relative minimums or relative maximums. Instead of using the first derivative, we're going to use the second derivative to figure things out. So, if C is a critical point for a function f of x, and once again, we have three different cases here. So let's look at case 1. Case 1 says then if the second derivative is positive. What does that mean? What does that imply? If you have a critical point where the derivative is 0, where your function flattens out, but your function is, if your second derivative is positive, that means your function is concave up. You have upwards curvature. So if I have upwards curvature, but my function flattens out, what am I working with? I'm working with a local minimum. So this implies that f of x has a local or a relative, sorry, we've been using the word relative, but they're kind of synonymous, relative minimum at x equals c. Case 2 is very similar. What happens if your curvature is negative at the critical point? That means if you have a critical point, but you're concave down there. If I have downwards curvature, that means I've reached a maximum. Here's our example. I have downwards curvature, but I'm reaching a point where the slope is 0, and therefore I have a local maximum. Third case, what happens if your second derivative is 0 at that point? Well, it turns out there's no conclusion you can make from this, and we just say it's inconclusive. And if you're searching for whether it's in the relative minimum or relative maximum, you'll have to just go to your first derivative test. So you can kind of see where the second derivative test is nice. Instead of picking new points inside the intervals, you can just use your critical points and plug them straight into your second derivative. But that's the second derivative test. It's a way to test whether critical points are relative minimums or maximums based off of the second derivative. And that takes care of 2.2. It's really just integrating our knowledge of the second derivative into analyzing graphs and analyzing functions. So go ahead and get started on the homework, see what you can do, and then if you run into problems or if you have questions, check out the examples video. Good luck!